This video will discuss three-dimensional modeling in ArcGIS 3D Analyst. Well, everybody, welcome to the world of three-dimensional. I guess the first thing that I'd like to discuss is, why do it in the first place? Now, there's a lot of analysis in GIS that you could use. You just do 2D, representations, and you could do fine analysis. The reason being is that this brings in the human element, and since we're such visual creatures, that's a good thing. There are things that we can suddenly see by creating a representation that is closer to what, say, a terrestrial environment is three-dimensionally, or looking at structures that look like they would look like if they were built. Say you're doing some modeling for urban development, so on and so forth. It is human beings getting a little bit closer to the data and allowing the human element to come on through. So what we're going to do first is this. We're going to look at DEMs, digital elevation models. We're going to look at modeling the surface, and also look at the origins of a lot of the data that makes it up. And then we're going to move on to the theory of, so how do you actually make something three-dimensional, and even look at how to put three-dimensional structures on the landscape. So, digital elevation models. Here, let me read this for you. The representation of continuous elevation values over topographic surface by a regular array of z-values, reference to a common datum. Wow, that sounds pretty exciting, doesn't it? In essence, everybody, you've got, just like any other GIS data, okay, you've got area data, but you're going to be bringing in this z-value is the height. So that's going to add that extra dimension, and that's what ultimately gives you that, that three-dimensional look. Now, as you see in point number 2, typically represent elevation, but z-value can represent other values. If you wanted to, you can make a elevation model map of population. And actually, those are very nice to look at because they quickly convey, by the way, not just population, but any other demographic information. So it could be other things too. Now, historically, when it came to digital elevation models, they were created through maps that represented the landscape using contour lines. Lines that had constant values of, say, a certain elevation. You've seen probably many of those, especially those of you who are maybe avid hikers, campers. Existed plates used for printing maps are scanned. In the very beginning, what they did is they took paper maps and they scanned them. And once they were scanned, you'll see that, well, vectorized and edited. That's just part of the process of putting them into the electronic world. The contours are tagged with elevations. Well, that's when you digitize, you actually give the contour lines that you had on the paper map. You actually, well, you recreate them and give them their electronic equivalent. And then finally, number 4, an algorithm is used to interpolate elevations at every grid point from the contour data. This is where, finally, once these paper maps were scanned into the electronic world, an algorithm will be used to finally start estimating what the surface looks like. And I use the word estimating loosely and without any fear, because when it came to those first elevation models, they were again, you had contour lines that were created the good old-fashioned way. Surveyors went out or however, and they put it into the electronic world, and so it was the system. The computer's doing its very best, their very best, to represent the landscape with the data they had. Now here we have an example of that. Over to the left for contour conversion, that's one of those good old-fashioned maps. And every time I make one of these videos, I realized how old I am, because when I was a Boy Scout, when I was going camping, these maps were the kind of maps that we used, and you could interpolate what the surface looks like, what's ahead of you. Well, anyway, that's ancient news. But if you take that map over to the left, you convert it into the electronic environment, and you tag each one of those contours with their elevations. And now you look over to the right, hey, look at that. Now suddenly, when you put it into the 3D world, hey, now we got a visual representation of that data. Now, aside from the paper maps, the use of photogrammetry has been very effective in providing the data that would ultimately become a digital elevation model data. With photogrammetry, okay, you're flying some instrument in the air, some sensor. It could be from an aircraft, a helicopter, it could be from a kite, it could be from, just as long as it's up in the air. Well, what you do is you start taking imagery of the area, and not to get too deep into remote sensing, but you could either take an image looking straight down, or you can tilt the camera a little bit. And if you tilt the camera a little bit and you fly your plane one direction down a valley, and then you turn around and you fly the other way with the camera looking at it from another way, there is a method that you, from that data, you can determine what the terrain looks like, and even ascertain elevation values. Now the problem with that is that, okay, if you're flying through a desert, wonderful. There's no vegetation. You're probably going to get some good stuff. However, though, you start flying over forests and stuff like that, or there's a city, somewhere. The question is, where does the city end? Where's the ground, amongst all the buildings? And this is just one of many kinds of images you can find. This is actually, it looks relatively primitive. It's just amazing how much photogrammetry the data the general public now has at its fingertips. And when I look at this, I'm reminded of when I was a college student. I took a class in air photogrammetry, and we actually got up in a plane and we did one of these missions, flew in the air and took images and all sorts of good stuff. One thing I'll never forget is when the plane was coming in for landing, to have a herd of deer run across the runway. And I thought to myself, yep, today's the day you're going to die. But, well, that didn't happen. The pilot took off again, and, well, I'm here making a video today. Okay, now, aside from making pretty images, three-dimensional images of a landscape, there's a lot of pragmatic reasons when it comes to calculations and other products that you can create using DEMs. Okay, number one, determine the attributes of terrain such as elevation at any point, slope, and aspect. Okay, determining, I guess you might say that's the number one thing people would assume when it came to the kind of data you can find. Okay, number two, though, finding features on the terrain such as drainage networks and landforms. Now we could look at things like, for instance, when it came to watersheds. Well, using the digital elevation model, you could actually use the computers, the GIS systems, to ascertain watersheds. And also, when it comes to certain landforms, that well, maybe, the question is, can you see the forest amongst the trees? Did you see that this was a certain large landform? On the landscape, things like that. Number three, modeling hydraulic functions and forest fires. Floods, what a terrible thing to have happen. But because of digital elevation modeling, there are a lot of cases where you don't have to actually have somebody on the ground and say, hey, by the way, there's going to be, this area is flooded, close off the roads and everything. During the flood of 93 in the Midwest, they used GIS to model the flooding, and even without sending people out onto the countryside, they knew where they had to put roadblocks because they knew where the roads were flooded out, and so there's that good function there. And also for forest fires, you could actually, looking at the landscape, you could determine, well, when it comes to the wind velocity and so on and so forth, you can model the direction of where the fires are going to be going towards. Number four, determining slope, aspect, and line of sight. Okay, these are things that you'll see when it comes to calculations of a variety of things in using ArcGIS 3D Analyst. They're very, very important. Now this ghostly looking image right here, this is a digital elevation model, but it hasn't been processed more, so that way you could see the surface as it should be. But this is what you're looking at right now. This is well, so if you see this in your travels through GIS. Just, this is a digital elevation model in its infant stages before any processing. Okay, let's do this three-dimensional analysis thing. For starters, okay, the variables. What are you looking at? What is it that you want to make three-dimensional? Number two, the z-value. Are you looking at well, it's your units of measure? Is it decimal degrees? Is it feet, inches? Are you gonna have to do any kind of unusual kind of ratioing or scaling or something like that? Those things to consider. And finally, the third point here: surface sampling resolution. How many known points do you have to create this three-dimensional surface? If you have only a few, it's going to give you a rather simplistic surface, versus if you have a robust amount of points or of value, then suddenly you start to get a surface that really starts to get closer and closer to reality. Now this image right here kind of brings that point to home. Here we have 3 points, and let's just say we're modeling elevation. We're right by the coastline, and you see 50, 150, 250. Well, you got those 3 known points right there. If, let's say, you had maybe just like 2 more, and you wanted to model, say, the side of a ridge or something like that, well, you're going to get something that is, again, simplistic. If you had, say, maybe 50 known points in the same area representation, well, it's going to look better. Well, everybody, this is the workhorse when it comes to 3D modeling within the ArcMap software that's available to you. ArcScene, it is where you're going to finally start seeing things three-dimensionally. And I bring this up not, well, number one, to introduce you to it, but also we're going to talk a little bit about another kind of modeling system. And just look at that nice little island there. Does that remind you of, like, if you're playing a video game? Does it, for those of you who we strengthen our minds through playing lots of video games, right? Well, you're going to see that the video game industry actually has a lot to thank the GIS industry for when it came to these kind of surface models that it was developing with time. This is another surface modeling approach, the three-dimensional TIN model, the triangulated irregular network model. It's simple. I mean, that it saves space. If you're not bent out of shape when it comes to looking at the fineness of a surface, there are benefits to it. And so, well, it's kind of like using between raster or feature data. It's like, okay, so why are you using it? Well, maybe I'm not as concerned about the surface, or well, the surface being as well represented as it could be. Maybe a general surface is okay, so on and so forth. So a simple way to represent the landscape. So just like when you're looking at DM, the more points, the rougher the surface. The more points, the rougher the surface. I got to use a better word than rougher. Well, anyway, we're going to move forward. Sample points are connected to form triangle. And in the next graphic, you're going to say, hey, wait a minute, that looks pretty familiar for those of you who like to play video games. The surface is continuous. One way or the other, it will create a surface that there isn't going to be any holes in it or gaps. And simplicity and economy, it is the poor man's version of surface modeling. And here's a tin model, and you'll see, just like in the previous example, we're looking at modeling the side of a ridge or something by the coastline. Well, now if you have those 3 points of known location, and then you connect them together like this, look at that, now you got that triangle that kind of represents surface. And let's take this to another level now. And there you go. Welcome. Now, once again, by the way, you must think I play video games all the time the way I reference it, but what's interesting about our society is that a lot of the things that we use for recreation, in particular like for video gaming, it played a major role in pushing forward computer technology. And so for those of you who are into video games or just you've seen this before, look at that. You've got those triangles that are connected together, and so my guess is you've seen these surfaces before. That, my friends, is a tin model. Now, when it comes to 3D feature generation of actually creating surface artificial objects that are going to be put on the landscape, like you see the city right here, it's actually a pretty straightforward method. What happens is you get a polygon, let's just, or well, polygon, let's just stick with that, please. And you give it that z value, but what you would also do is you would provide a method when you, well, through ArcGIS, through a 3D Analyst, you can identify it as having height, and what it'll do is, this considers the surface of a roof of a building, it will generate the walls, so it'll give it that other dimension. And in the attribute table, you're going to see now, when it comes to 3D objects, you're going to see that the z value will be identified also. And some other interesting things you can do in 3D Analyst, when it comes to a surface view, you can drop yourself down onto the surface, so that way you can look around and see just what you would see if you were at a certain point. And that's kind of nice to do. But also, you can do fly-throughs. And here you see this cute little bird, and you'll be able to actually animate flights through areas. So if you want to play fighter pilot and fly between the buildings and stuff like that, you can do that, and you could actually record the experience. That way you could share it with your friends. But maybe, just maybe, you want to use this for more productive reasons than that. I think that's okay if you do. And just to conclude, even though to the left, okay, elevation, that is considered when it comes to 3D modeling, the classical, thing that you want to see three-dimensionally. Note that the middle graphic here, precipitation and soil pH, any one of those can be turned three-dimensionally, so that way it's easier for people to analyze the data.